Okay, my friends, this is another shocker du jour. They are looking for neutrinos. And they dug 2,300 feet down and created this detector so that it would stop all the rays from the sun from interacting way down there. They think they're going to be free of the sun's influence, which here they claim trillions of them are passing through your body every second. And all of these things I disagree with. And I also disagree with the fact that they have to go down here this deep to find neutrinos and have to spend all this money. I'm going to show you, I think we already found them. And I'm going to show the evidence to support what I'm saying. And then secondly, I want to have someone tell me what a neutrino is. What is a neutrino to them? Because they're talking about muons, which are neutrinos. They're talking about electrons, which are neutrinos. What neutrino are they looking for? And then they have a tau neutrino, they call it. Those are the three flavors. Well, which one are they looking for? Or are they looking for some exotic flavor? I can show you these neutrinos and these flavors from the experiments we did using light, which is basically the smallest particle there is except heat. Heat is one step below. Two bits of heat together make a photon. Two dipoles. Let me explain this to you. And I think the evidence that I'm going to show you, it has to be examined because it may lead to literally free energy. Look at this. Set up is to collaborate 74 institutes, 700 individuals, led by the Chinese Academy of Sciences Institute for High Energy Physics. It should operate for at least 10 years, hopes to collect enough data over that time to shed some additional light on characteristics of these enigmatic particles. Well, let's look at what I have to show, and who knows, maybe it can help, maybe it's just silliness. But I think I'm showing stuff, it's coming from light. We're seeing the particles. The particles do exactly what they were supposed to do, the same particles that they're showing in Fermilab and CERN. I went to the University of Geneva online, and I showed them what we were doing. That was 10 years ago. And they finally agreed, yes, you can see these things with CMOS, and now everybody uses CMOS. They upgraded to use CMOS at CERN. This right here is a subatomic nuclear, because it's inside the nucleus particles, explosion. And it breaks the white from the black. Now, in this particular case, some of the black is allowed through, pushing the white. You see the black here? That's the dark matter. And that has mass. And the white particles are moving ahead of it, and they are just nothing but energy. Now, you see the distances out here. These are called Whistler waves. And a Whistler wave is, if you were way out here, when that went off, you'd hear as it went by you. It's in the audible range. Then you see how tight these are? That's in the matter range. This is just in field to field bumps. This is matter to matter bump and pushing. Now, if there was a house right here and that went off, if you could watch it slow enough, you'd see the house would just vaporize until all of the white went past, and then the black would hit the house and the house would go flying. I'm going to show you that happening right now. All right, here it is. This is atomcentral.com, Teapot Apple II House Atomic Bomb Blast. Now, what you're going to see, I have it running real slow, and I have the sound off because it would make some terrible sounds. Now, it's coming into where you have a blast. All right, first of all, here's the house. They have a hardened enclosure facing this way. It can't damage the camera and that kind of equipment. They're setting it all up. Now they bomb, it goes off. Boom. I'm going to stop it right there. The bomb just went off. You see how brilliant this is? Now look back here. Anything that's combustible Combustible means it can absorb energy, and the bonds can break in the matter that's there. The steel won't do this. The tank won't do that. But a shield, you know, the roof, watch what does it. All the insulation on the wiring, the transformers won't do this because they're metal. Metal is gonna get hit, but it's not gonna combust. It's just like if you took a blowtorch and you put it on there, it wouldn't do it. You put a blowtorch on here and it does this. So here goes. Now, look at what's doing there. There's nothing even being pushed back. That tiniest little push. You see that? It's completely combusted. Everything here that can burn is already gone in the blink of an eye. And I mean, I'm talking a blink, a very quick blink. That didn't go. These didn't go. But all the insulation, all of the roofing, all of the facade, everything that has the ability to absorb these fields. And once they get the fields in there, just everything combusts out and burns and goes away. It actually breaks down into other, you know, gases. Now the black is going to be coming. So here we go. Boom, there's the black. Whoops. There's the black. So what happened was the nuclear bomb in the center is the black. And when you shoot off a nuclear bomb, you force everything back inside so tight that the release is just stunning. And the first thing to go, of course, is going to be the electron neutrinos, because they coat the core of the black. And they go first, which is just exactly what I showed you. Let's look one more time. Here's the house, everything's fine. They're putting in just what you'd have in a regular little area to see what is going to happen when you get hit by a nuclear bomb. Will not burn, will not burn, will not burn. Everything else combusts. They take the truck out of here, the hardened enclosure looks this way, and just watches what happens. And this is what happens. The first thing, I'm just going to let it roll this time. The first thing that happens is you get that brilliant flash. Look, everything. Look at how black it looks back here now. Because everything here is so energetic. Everything burnt up. There it goes. Now it'll turn around and come back because there's literally a hole back here. See, look. It turns around and comes back. There's a void in the atmosphere after the bomb goes off. Okay, before we start, this is going to be a little bit of a technical discussion about these neutrinos. Now, I have an argument with them about what a neutrino is in the first place. They're talking about muons and electron neutrinos and tau neutrinos. They think they understand something about those. But then they go on to say neutrinos are one of the most enigmatic particles in the standard model. The reason is they're so hard to detect. It's really dark matter. All right, it's not normal matter, it's dark matter to them. It says the main reason is they're just hard to detect, despite the fact that 400 trillion of them created in the sun are passing through a person's body every second, which I disagree with that. However, they rarely interact with normal matter. That's just not true. They are normal matter, they just don't understand it. It makes them understanding anything about them difficult because what they're looking for does not exist. Hold on one second. Okay, they say there are three types of these neutrinos. They're the electron, the muon, and the tau neutrinos. Each has slightly different characteristics from one another, and they have the ability to shift and flip and so forth between the different types. They call it oscillation in the language of particle physics. I'll show you that right now. Okay, this is what they consider the muon neutrino. Is it just a black ball? And this is what they consider the electron neutrino, which is, it creates electron showers. Now, why does it create electron showers? In the case of Cherenkov radiation, the energy of the particle coming in is going faster than the speed of light for the medium that it's entering into, so it leaves a trail of this blue shower that comes through, because literally the electron's field is banging into every other field, and they shower into a big spray, and it's an enormous spray. This does not do that, the muon. So you got the muon neutrino, and you got your electron neutrino. The tau neutrino is not fully formed into what you would call a Dirac neutrino. A Dirac neutrino means the black and the white. This is black, this is white. This one never changes, has all the mass. This has no mass and showers like crazy when it gets confined and smashes, and that's what creates light. So these are from experiments Rod Warren and I did, and this is the muon neutrino, the black ball, which is the black all over the place here and all over here. And then you have the white one, which was attached. They were just standard attached and exploded into the electron shower. And that is exactly what they call them, the muon neutrino and the electron neutrino. Black ball and white showers. Black balls, white showers. Why did that happen? Why did they separate? Because normally they're attached and they are tight. The white can get small and it can get big. It was able to squirt through this very perfectly tuned Venturi, and the black couldn't get through with the white. It stayed back and the white showered through. And then it reattached out here and created what they call Higgs fields. Okay, this was the announcement in 2013 that they found the black particle and the glowy particle, and the black had a glowy ring around it, the color of whatever light it was. And these are the smallest particles they could find. And this is from 2013. Now, and it said they had the exact same characteristics. This has all the mass and never changes size. That has all the energy basically, and gets big and gets small. And that burns stuff, and I mean burns. And you can see this very easily in a nuclear bomb blast. Extremely easy to see. This is the first particles that come out, and then behind it the black ones. The first ones that come out just make buildings smoke. They don't even move. They just smoke up because of the energy that's being absorbed. Just energy, no mass. That's the key with this one. But when this one comes, it's all over. All right, so they say there's the electron, the muon, and the tau neutrino, and those are the three types. Well, let's look at what it says a neutrino is, and what they are looking for is something that just doesn't exist. All right, so they claim there's three types of neutrinos. Well, this is Dirac neutrinos. There's a black one and a white one. This is backwards. This has no matter. That has all the matter. And this is when they're fully formed. This they call the Majorna, neutrino, which is not quite formed yet. And I can show you this. Now, why they changed the names of it to these new neutrinos, I don't know. But what happens is this is the flipping and flopping, the oscillation. Everything's a Dirac. So you have a black and a white. Now, as the light comes in, it's not really formed as light yet. You can't see it. The only time you see it as a really fully formed photon is when it's interacting with something that's really like matter. And what is matter made out of? It's made out of a shield of fields, yes. And that's the issue here. This thing thinks it just hit matter, but it's hitting the reverse bounce back field. Turn it into a photon right in the middle of the air. So here's your tau, or your whatever they want to call them. And it flip-flops, oscillates. You see it's this way and this way. They always are either this way or this way. They're never like twisted this way or that way. You see it? You see them? You see them up this way? Always that way because of the polarity of the Earth. And the same thing with these. They spin this way. I've only seen them one time barrel roll, and that's because we forced them to barrel roll using this 2 lasers at the same time through the same slit, and one of them made the red just tumble. This is oscillating right now, just like they talk about. They oscillate, they can flip, and they do this and that. But there is nothing more than these 2 particles, the black and the white ones. They're looking for something that doesn't exist. I'll show you what they're looking for, which they call a neutrino. These are neutrinos. Just all it is a muon neutrino is the black, electron neutrino is the white. We split those, yes. You can split them apart, no problem. You see, they found these over 10 years ago. That's the same particle right here, and that's the same particle right here. This one can get big and small. That one never changes. That has all the mass, that has all the energy. And that's it right there. We accelerated it using a Venturi and accelerated this particle right here. Forced it to accelerate. And when it did, it interacted with all the particles in front of it and pulled itself right out of its own magnetic field, just like a jet pulling itself out of its own wake. And then right here is where the photons displayed, right here. You would never see that. It wouldn't happen until it hit the wall and bounced back. Then you might be able to see it. But this thing thinks it hit a wall right there. It thinks it hit a wall. So do these. These are coming through the air. They're doing nothing because there's nothing to hit, to speak of. They're easily sliding through the air. This one is accelerating. So it's creating that wake, which is the field. You know how they always say particle wave duality. Well, there's a wave because it's the field has to move and the particle's in the center. There's the particle. And this is the particle right there. And this is what happens at the Venturi, which is this spot right here. Oops, let me back out here a little bit. There's the Venturi right there. And here it is right up close. And here it does create the muons and electron showers. Muons, electron showers, exactly what they're looking for. All right, that's Cherenkov radiation. And we are faster than the speed of light. That's accelerating. So they are right. It's faster than the speed of light. And when it interacts with that, and the only reason it's getting faster than the speed of light is because of the Venturi. When it interacts there, it's split time. And the black just can't get smaller, so the black stays back, Jack. And the white just keeps on going. And again, I've shown that in these other ones. This one here is a similar situation. The white got out in front of the black. And the black just kept pushing. And that's exactly what happened at the house, when the house burnt down. Now, the green is exactly the same as the red. No question, no difference whatsoever in the particle. And this one's getting ready to flip, which is oscillation, the muon wobble, they call it. Oscillating photons, oscillating muons, oscillating oscillators. And we don't do this. We don't smash things and have just monstrous chunks of things and all kinds of debris, which they call the particles do. It's not necessary. We started with the smallest particles. So they're showing them here and here like they're different particles. They're not different. They're the same particles. That just has less energy than this one. Simple as that. But then they have all these fragments. They have huge X particles. They have little bitty ones. They have the tiniest ones. They have all kinds of globs of stuff. We don't have that. We never started with anything bigger than that, which is the light. That's what we started with. All right, which is where they see the same particles, only they see them one over here and one over here. They don't realize that they are part of the dipole. And in the dipole, there's about 1,839 dipoles make up one proton, which would be one big ball, which is the smallest stable building block. All right, that's the smallest stable chunk where there's enough electrons surrounding the dark matter in the core that it becomes stable, right about at that exact amount. And then they keep adding that exact amount every time, or right in that area. Neutrons, protons, they're basically the same thing. There's just one of these difference. A proton has one less than a neutron. A neutron would have all of these. A proton has just one missing. So what does that mean? A proton wants to either add to something and share that proton share that hole with somebody else's electron, or it wants to take on an electron to become stable. It's looking for stability, which means it has to fill all these layers that are loose parts hanging off, that are going to end up attaching to something else or splitting and falling off. I hope that makes sense. But you got to understand dipole electronic flow theory. It's a 5-minute read. There it is right here. That's it. Inside of all of these charged particles, which are the closer to the core, the more the charge. The more the charge, the higher up the frequency. Blue is the higher charge, then green, and then red is sort of loosey-goosey. The red and the green we can see. The blue is too fast to really work with. But the red is quite easy to see and photograph and everything using CMOS. That's the key. So these are the tau, either this way or that way, never this way. Same thing with the photons. However, at one shot we put the red and the green through at the same time, and the green is so much more powerful and faster that it made the red tumble. Now, this is the Venturi. These lines back here are reverse EMF, they call that, electromotive force, banging backwards. Normally, they're only going to go this way. This is an unbelievable amount of reverse energy because this is a gigantic explosion. In the subatomic realm, this is as big of an explosion as you can get. That created fission where the black separated from the white. There is no question about that. You can't dispute that. And this is where the black came back against the white, because they always want to be together. The black just seems to be everywhere. At first it really puzzled me, but they do say the black just seems to be everywhere. They just can't find it. They don't understand it. It is dark matter, and it's part of us. It's part of every light particle is dark matter. Half of it's dark matter, half of it's white. And that's this right here. Every dipole is just like that, only it's opposite. This has no mass, and that has all the matter, all the mass. And this is, I guess they would call it tau, which is in the middle of doing this. But everything always is polarity, straight up and down, like these ones here, straight up and down or this way. And even when they're going off to the side, they still spin this way. They don't spin going like that. They spin going like this, which is an interesting characteristic. And then we did tumble them. Now check this out. This is outrageous. These are the green photons. And you can see the little red splotches in there. That could be the neutrino they're looking for, because it's not attached to the black. I've never seen it by itself, the white just hanging around by itself. But this does appear to be the glowy part of the red laser. That comes in with a black and a red attached together. I'm just seeing little red spots there. What this means, I have yet to determine. However, we do see the green is still structurally solid, just like it was when it came in. Now, this is where the two of them come in together at the same time. You see this red splotch just twisted down this way? That's all the red particles. Normally they would splash out like this. Well, the green is so powerful that it just slaps it down. Now the green normally wouldn't do anything until it came way out here. And then it would start displaying because it's so powerful. The red automatically, instantly, basically starts to splash out because it's just not as directionally strong. That would have been the normal, and then out here it would have splashed off. All right, you see this? This is the red and the green together at the same time. This is what the green would normally do. If it wasn't coming through with the red, it would come out so strong that it really wouldn't start to react until it got pretty much out here. And then you see these streaks because they're interacting with the black particles at that point in time. And they're turning into photons again. Originally they came in as photons, they're turning into photons again. And there's all kind of little scraps going on here. But you see them, they're always this way or that way. You see it this way or that way. Even they're kind of globby looking things going on there. But this is the mix when it comes back to being light particles again. Now, what we're going to see now is the blue, the red and the green together. And the red has no energy to speak of compared to the green, and neither one of them have any energy compared to the blue. So here's the two of them coming through together at the same time. The red would have just went and it would have come out to about here maybe, and by that time it would have been completely reabsorbed. And it's only out to here, and it's reabsorbed already. There's almost no continuation here. Well, there is no continuation. That's as far as it's going to get. Now you see these? They're spinning around in a circle. That never happens. That is a never ever happening event. Never ever. And that's because this is coming through like this. Sort of loopy slow. Bada-boom, 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 bada-boom. And this is coming down much faster, and it just throws them around. Because it's field to field. So it's field to field, but normally it's straight ahead, and it's always the polar to the Earth, except in this particular case. And you see up here, we got some little red goopy stuff up there. Somehow the energy has separated, and I've never seen that before. Because there's no black attached to that red. You see that? It's still up and down, and these are still sideways, and these are all the pixels that are inside the CMOS. This is very cool stuff, I think. And then again, the green whacked way out there just like it would have normally, and you can see all the particles. They're all the same. And again, this is, I would think they would call these the taus, and that's probably another flavor of tau, because they say they can flip around into taus, and then they can get real taued up this way. And you see, straight up and down, it's just, all I can tell you is as they come forward, if they're not fully formed photons, this gets longer and longer. You see it when they're right up close to the Venturi. They're hugely straight up and down, which basically is a wall of black particles coming back at these. That's when you get light, is when you get the white hitting the black. You see how white is it hitting the black there? Up here, it's a little further up, is not quite as energetic. So I think this solves it, but let me show you what they claim a neutrino should be. And I say it doesn't. Well, let's take a look at it. Then we'll make a decision, okay? How about that? All right, this is from the same place that I get my alerts from, a lot of alerts, and they say, what are neutrinos? And they're saying they're neutrinos are a type of particle similar to the electron and belong to the lepton family of fundamental particles. Neutrino is distinguished by a lack of charge and a mass that's virtually non-existent. Now let's think about that. A lack of charge. I disagree with that totally. If it has virtually non-existent mass. All right, that's the one that has the most charge is the electron, which has no mass. The muon neutrino has all the mass. So this is exactly backwards. And it says it's emitted as a part of the beta decay process, turns neutrons into protons. Well, that's what I showed you before. That's a neutron right there. It's got 1840 exactly particles. It's neutral, neutron. Well, you take one of these away, which is a dipole electron, you have a proton. It's the beta decay, one of these goes somewhere else, and it turns it into a proton. Yes, I agree with that. Neutrinos are one of the most abundant subatomic particles in the universe because they make up light. Tens of billions of them hitting your fingernail every second. I don't know about that, but there's a lot of them. You wouldn't notice because the neutrino is only affected by the pull of gravity. Now they get into this nonsense about it's only affected by the pull of the weak subatomic force. No. Neutrinos are strong as hell. They are pulled by gravity, yes. Absolutely. And gravity, the Earth is made primarily out of dark matter as far as I'm concerned, because all of the light wants to hit the Earth. Light comes down to smash into the Earth. That's where light comes from. But it's carrying its own heavy little particle too. And they're coming out of the sun in tons and buckets, yes. Absolutely correct. And then they come down and you see them in the sky coming down, basically, sometimes in the northern lights and so forth. But anyway, they're coming down, interacting with all the particles and giving off energy as they come down, and eventually they hit the Earth and they're incorporated into the Earth. Every time one hits, you get another one, another particle. So anyway, they're calling them ghost particles. You have no idea that they're near zero mass. Well, no. The particles they're talking about, well, here's the key. One of them has no mass and one of them has all the mass. Which one are they looking for? Dark matter is what I think they're looking for, and that's the one that has all the mass. So it says their slippery nature makes them ideal subjects to study distant cosmic events, and even made them a candidate for the mysterious matter known as dark matter. Well, it's not a candidate, it is dark matter. The black part is dark matter. When I say it's dark matter, I can pretty much prove it. What does dark matter do? You can't see it. You can't see it. And the reason you can't see it, it's always behind the glowy parts, which are the things that bounce back at you. It's always inside is where the dark matter exists. The only way you can see it is if you can put it on top of the white glow, which we did right here. All right, the dark matter is the muons. Dark matter is the muon neutrino. I don't know why they couldn't understand this. It has all the mass. It's all the mass. This is just the energy. And here's where the black is all the mass. Here's where the energy takes over. Electron showers. Now, the only reason we can see that black is it's on top of the white. The black never changes size. You see the size of these particles? They're all the same, although they look different sizes, but they're not. The reason they look different sizes is they're shadowed differently from behind. You see them all over here? It's the exact same particle. Now, at the Venturi, they split and they back off because they can't get through. You have to tune this correctly. Once it comes out the other side, the black just starts to jump right in. See it? This is all black. This is saturated with black. You don't see it. You don't see the black here, but it's there. The only time you see it is when it covers up the white. Dark matter, which is the muon neutrino, is my claim. Dark matter does not emit, so it's not going to send off anything. It doesn't absorb. It doesn't absorb anything that I know of. It doesn't emit, absorb, or there's another thing. It doesn't do anything. But it's strongly, viciously attracted to the white. And if you can pull those two apart, which we did here, that's a subnuclear fission and fusion. All right, that's the particle they're looking for right there. That's dark matter, the black one. It's the muon, normally attached to the white one, as I showed you. And they found this at Fermi-Lab. They found it everywhere. CERN. They know these two are there. They just don't know they're always supposed to be attached. And they don't know about dipole electron flood theory, although I think they do know. They just don't want to talk about it. And this is a 5-minute read, tops. Everything, the glowy ones surround the dark matter. These are the ones that have the energy. These are the ones that have the mass. Simple as that. These are the two particles that make everything there is. Differences between the standard model. Gluons, they call them gluons. I call them dipole electrons. Dirac electron, neutrinos, whatever you want to call them. And we can split these apart. Two back to back, these are nothing more than heat. The white one all by itself is raw electricity. And all two of these back to back make a photon. If you took 1,839 or so of these particles and put them in a ball, you would have a proton. And 1,840, which is a neutral number, you would have a neutron. This just explains what each one of these things does. And here's what the difference, it changes to science. You know, the redshift, that's not really true. There's a lot of things that just aren't true because you have to look at really what matter is made of. You have to start there. And that's what it is. And it explains virtually everything. Now don't forget, these are all from actual experiments. Just simply using CMOS, which is complementary metal oxide silicate detector in smartphones, and lasers. And a Venturi. And a Venturi is a very, very simple device. It's nothing spectacular. It's like this. It's a narrowing. Now, you would have like this coming across, like a funnel coming down here. And all that stuff would funnel in. And at the pinch point, you get this explosion. If you tune it correctly, the black particles, which are the fixed particles, can't get through. They have to bounce back. But the white can get through, and that's exactly what happens at the pinch point here. Right through. So, and there's all kinds of designs. Now, Rod was working with nails and pins and all kinds of things, single slits, dual slits, 3 slits. I was working with screens and sort of novel little things. I was hoping maybe I could make a whole batch of Venturis at one time and just, you know, really splay it out. But Rod, he was the guy. He's virtually, well, most of this is what Rod did. A few other things from some other people, but it's just phenomenal work. Phenomenal work. And this was from the Russians in space. This was, I think, 2015, 2014. They found charged particles, created this, a black hole. Now, there's a couple reasons, and I say really, they couldn't figure it out. During the experiments, we contacted the Earth guys who couldn't believe it either. Nobody could figure this out. One guy locked himself in his office for 3 weeks. They said, that's what they said. Now, I think I understand it. And I think I understand why we're seeing these glowing particles here, that they're just not going to glow by themselves. They're sending light into this vacuum chamber that they put in charged particles. And they're charged, yes, absolutely they're charged. However, they, I'm sure, sent light into this. It doesn't bounce off of dark matter. Dark matter doesn't emit, absorb, or reflect. None of those things. So it's just 100% black. Nobody can explain that. And then all of that white surrounds it. Well, why would that be? If they send an energy into here, it's energizing the things that are not black particles, because they send off energy back when they're getting hit. So all of the particles that are white start energized coming back, and they end up pushing the dark matter to the center, giving you this black hole effect. And it just jiggled like this. And then they showed some other experiments. They were looking at pinch points in atomic vapor, basically. And I know it was all swirling like this. And the reason was they were putting in energy. They were sending energy into it. It wasn't just swirling there for no reason, I don't think. This was Plasma in Space Experiment, English subtitles. And like I said, this goes back quite a ways. I did my homework on this, and I'd like to talk to somebody about it, because I think we could maybe get some free energy. And again, this is not something I made up. They found this at Fermilab in 2013. And I tried contacting that, and that was very discouraging, I can tell you that. I sent them, I said, I found your particles, the same particles we found them using light. Can we talk? And I was really, it didn't go well. So I think I've shown something here that has merit. These are the particles they're looking for. I'm almost certain the muon is this neutrino they're looking for. All right, this is about Cherenkov radiation, and it is used to detect neutrinos by observing the Cherenkov light emitted by charged particles, which are electrons or muons, produced when a neutrino interacts with a detector medium like water or ice. And that's because it's a denser medium, and as the particle comes through, it splashes through, creating the electron showers. That's the Cherenkov radiation. Well, we did that using the Venturi. Same. It's just we changed the speed of the electron. So we didn't make a change into a different medium. We made it faster in the medium it was in. This is always because it's faster than it should be going. All right, this is really quite simple. They're sending the muon electron showers through, which is the high energy particles given off by nuclear radiation. And they want to slow those particles down so that they don't go and smash somebody and kill them. So they put them into this heavy water. And this water will slow that light down. And when it does, the muons just go by themselves, and the electrons turn into streaks of showers of light produced, called the electron showers. And that's what I show in our experiments. And we didn't have to hit something heavy water. We accelerated the light much faster than it would be in the normal world by using the Venturi. So we didn't have to put in heavy water. We did it this way, by accelerating the light. Same thing as hitting something here that was pushed back at it, because here's the same thing right here. It's just like we hit heavy water here. It's just because we're going way too fast for the rest of the world. And at that point, you create your muon neutrinos and your electron neutrinos. The exact same thing happens in Cherenkov radiation. And they know this. They found these particles. They know those are the tiniest particles, because these are nuclear decay particles that are hitting that water and slowing it down. Okay, so we're talking about Cherenkov water detectors. And this is University of Sheffield, and they're talking about neutrinos are weakly interacting, so in order to acquire a good neutrino data sample, you need both an intense neutrino source, which we have, to maximize the number of neutrinos, a very large detector. Well, we're doing it in a different way. But you want to see as many neutrino interactions as you can. They're talking about seeing like 40 to 60 a day, something like that, at this huge thing they built underground. Now, we're using water as a detection medium as a way to provide very large target mass at a reasonable cost. All the world's largest neutrino detectors are water Cherenkov experiments. They're all using Cherenkov to detect the neutrinos. Here's how it works. They say, wrongly, nothing can travel faster than the speed of light in a vacuum. That means you can't accelerate light. We obviously accelerated it, and it slows down. They know it slows down, but they never knew you could accelerate it. We accelerated it. However, when light travels through a medium such as water, it's got to be transparent, such as water, its speed is slowed down by the refractive index of the medium. What it does is it's bouncing through that. There's still some resistance to that light going through there, and it'll slow it down. All right, the refractive index of water at room temperature is 1.33, so light is water is traveling at about 3/4 the speed of light in a vacuum. Well, let me show you this. You see this? This is light just as it's beginning to accelerate. You wouldn't even see this if it wasn't starting to accelerate. You see how this is starting to glow? It's hitting all the other fields in front of it, all those particles. Normally that would just sort of ease its way through there. But because we are accelerating it, and here's the acceleration in full-fledged, pulling itself out of its own wave. And this is where the explosion happens. Now, they agree exactly with what I'm showing here about neutrinos, but they can't understand that you can accelerate light. We didn't need to hit a medium, we accelerated the particle. It was exactly the same effect, only we did it much more elegantly. Now here it is right here. The effect is similar to an aeroplane traveling faster than the speed of sound in the air. You get an optical boom, which is in the light realm, analogous to the aircraft's sonic boom, which is in the sound frequencies. In effect, the particle outruns its own electric field. And they show it in a diagram somewhere. I can show it in reality right here. There's the particle outrunning its own electric field. That, my friends, is the neutrino effect. All right, I think I've shown we do the same thing as the water detectors, only we accelerate the light. We don't have to hit some medium that slows the light down. All right, this is this detector. It's known as the Xiamen Underground Neutrino Observatory, or JUNO. It's located in between two huge nuclear plants at Zhengzhang and Taizhou. This is, I believe, China. Both of those fission plants, which means they're splitting atoms, they create their own artificial neutrinos in addition to the ones created by the sun, meaning the general area should be awash with barely interacting particles. Well, they just don't understand the nature of the particles, I don't think. I'd like to speak to somebody about it. I'm showing the particles. Now, that's despite the fact that, like most neutrino detectors, it's located underground, 700 meters underground. The physical bulk of the Earth's crust is meant to block most other particles, like muons, from getting to it, and at other installations like IceCube, it does a pretty good job. You're not going to radiate from the surface down to here, but you're still going to have nuclear decay. I don't care how you do it. You're going to get nuclear decay, and you're going to get a snap here and a snap here and a snap here. On the surface, it's more reactive and it's more interactive to the particles that are hitting it. Yes, 100% certain to that. Way down here, you're going to have a lot less reactivity, but it's still not going to be zero. All right, so they're looking for tracking, but what they're going to find, they're not going to find something coming down from up above or whatever they're looking for. They're looking for the oscillations. They've got the electron, the muon, and the tau, each slightly different characteristics from one another, which I showed you these photons. They have the ability to shift between different types, yes. as I showed you, they come in this way, then they turn that way, and then they turn into photons. They oscillate in the language of particle physics. I think I've shown pretty good evidence to support my side of this thing. Now, they're looking for this to support the Big Bang and all that nonsense. Well, I think we got to start back right from the beginning again and say, how did all this stuff start? Because I'm going way back to the beginning of everything, my friends. And, you know, looking for me, I'm a material researcher. I like to see the material, and I found it. And we tested it, and we did experiments on it, and we showed the results of it. And these are the things they're looking for. And it's a hard time for science to take a hard look at what they didn't take a look at. And that is dipole electron flood theory. If you don't start from here, you're just nowhere. Because you don't even know how, they can't account for gravity. They don't know how gravity happens. I'm serious. This dark matter, all the universe is made basically of dark matter, and they can't account for it because they don't know what it is, and they don't know how to look for it, and they're coming up with all these projects and things. Now, I'm contacting all the people that are involved in this that I can find. There's one here, I just sent something to him. Now, this is what he says. He concentrates his research theoretical high-energy physics, more specifically on the phenomena of physics that lies beyond the standard model. That's my stuff. And he's saying that there's evidence, no question whatsoever, that there's things that are different than we are being told. And we have to look for those answers. He's saying there's no well-defined answers yet. But there are certain things that are pretty solidly supported. Strong evidence that dark matter is not made up of any of the fields of the standard model. Standard model does not account for dark matter, it is correct. Hence, very likely new fields with unknown properties interactions exist. Absolutely. Secondly, beyond reasonable doubt, neutrinos have non-zero masses. All right, so the black one has a non-zero mass. I think the white one must have something, but I don't know. Non-zero neutrino masses are not allowed in the textbook version of the standard model. He's right. He's right about all this. I'm hoping he contacts me back. I sent something to him, hoping for some support on this. I send it to all of the universities and whoever makes statements, I usually send something to. Very rarely does it either doesn't get to them or they just don't have an interest. I don't know why, but we'll find out if this guy does. And he commented on this. That's why I got a hold of him. Somewhere down here, he commented on it that it's. And it said he wasn't involved in it, so I'd have to find it. Hold on a second. See, there's a potential discovery how often types change from one to another, which is their oscillation frequency. Well, we can see that in the particles that I show right here. You see how the black is down in the front and the black now is down in the back? That's an oscillation. That's the flip. And why does it do that? The white coming through here charges up and gets so charged up that it's pushing hard, it flips to the back. This one comes forward to become charged. And I can show you that they have different charges, and the one that is in front is the one that gets charged more than the one in the back. Don't forget, these are the two particles. Here they are. They're coming forward through the air. If you can see those little white particles there. You see those little white ones right in front of the glowy one? That's the glowy one. And they're glowing because it's the lead particle. It's the lead energy particle. These have no energetic value. They just don't seem to have an energetic value. All they want to do is hold on tight to a white particle. It doesn't matter who it is. And there's no such thing as entanglement. This got stuck with this one. They're married for life. No. this can break away from that one. Now this one's not charging up because it's behind the black. It's going forward. The only one to charge is the ones that are interacting with other particles, hitting them, pushing them, get out of the way, get out of the way, you get out of the way, you get out of the way. And so this one's getting bright and glowy, and that one's dim, and eventually, as soon as that gets big enough, it'll go whoop, and that one will come to the front and start to charge up, and this one will discharge. That's what makes them spin like that. And here it is spinning right here. Well, not in this one, I'll show you in a second. But it's going so fast you can't see the spin, but I can show you the spin in this one here, where it's in a real stretched out mode. All right, now coming in, it's coming in as the tau, which is a not formed photon. It's an unformed photon. It still observes the rule of polarity to the Earth. You see how it's flat like a pancake, and then it's straight up and down like a board? These have already formed into photons because they're dead straight in line with the Venturi. And they feel like they hit a wall. These ones up here are still these other flavors, and they can get very energetic. And they stretch all the way up and down like that. It's kind of crazy. But these are different forms. I would say these are the taus. These are the photons, and inside of the photons you have the muon, and electron, neutrino. Now, if you just had half of that, the black and the white, that's heat. That's actually heat. When you heat something up, it takes on more of these dipoles. And it actually gets hotter, it gets heavier. Seriously. When something, unless it's a gas, gases expand. Something that's solid doesn't expand, it gets hotter, it gets heavier. And those can just leak out to wherever they're more accepted. There's not enough of them. So it'll say, you can come over here, we're cold, we'd like to have you come over here and warm us up. And they go. And that thing, whatever it was that was hot, turns cold. It's as simple as that. It's the flow of the dipoles. Light is a different story. Light is pretty stable. However, when it hits something, it creates energy. It depends on the intensity of the light and what it's hitting. That's a whole big subject of what energy transfer really is. Because it's totally different depending upon the speed of the light, the medium that it's in, the thing that's hitting, the reflectivity. I mean, there's a million different things. So that's just the way life is. Okay, so they found these 2013. Basically, so did we. This phone that we were using to pick it up goes back to 2012. And when I saw that, I got a hold of Fermilab. Didn't go too good. And here's Fermilab again saying that empty space isn't empty. These particles are light. Light is particles. They're mass. They have mass. Light has a mass. And the universe is saturated with light. All right, every particle of light has a field around it. And it's nothing but fields, it's just saturated with these particles. Plus, there's all kinds of other things out there, dust and whatnot. Who knows what's out there? There's meteorites and comets and asteroids and who knows? Everything is out there. And it all has mass because it all has the dark matter, that black ball. Or is this one right here? This is the mass. That's the mass. And they say the same thing at Fermilab. That's where it has all the mass. It never gets bigger, never gets smaller. This one can get big, can get small, and I show that in extreme detail right there. This has the glowy edge around it. Yes, it does. This gets bigger or smaller, depending upon how energetic and what it's hitting. They just don't know what they're looking at because they end up with a particle zoo, which is this, just all kinds of stuff. We started there, so we know exactly what we see. We started with 2 of these, and each one of these is a little magnet. And so all it is two magnets back to back, a black and white, black and white. That's what a photon is. I hope I made this crystal clear. This should be investigated. This is not nonsense. It's very simple to do, and there is no ability to patent this. You can't patent this. I made this completely open to anybody, and I can't patent it either. It is just available to be used. This idea of using the Venturi with lasers to create excess energy, and I believe it's going to create an unbelievable amount of excess energy. I have shown the diagrams, and from CERN, not from me. All right, you see this? I think this is from CERN. I'm not certain, but it's from one of the top labs. They show the electrons coming in, very few. Low energy showers are down here. Then you got the high energy showers up here as it comes out through the Venturi. These are the muons. So these are the electrons. These are the muons. The muons hit and bounce back, and they basically can't get through the Venturi. Here is my proposal for a free energy device. Very, very, very simple. And you could put it in a box like this, carry it around, no grid, no nothing. And it would be not dangerous because we were working with particles of light. Venturi would shoot it in through, the laser would shoot the particles in through the Venturi, and only the white would come through. All right, so, and it would create these huge high energy. All right, now those are photons. They're in the form of, not actually photons, they're raw electron neutrinos, which is electricity. And it would force it down through a diode, which would be a photodiode. Photons, dipole electrons, which are the electron neutrinos, forced into battery, whatever you want. And you could have thousands and thousands of those in one little box like that. You could select between any kind of voltages you want, any kind of AC, DC, whatever you want. And this is not from me. They're showing from low energy to high energy. Now here's another shower, and this is my little proposal. You could put that in a box like this. You have a floating ground inside there. You carry it around in the woods and put it anywhere you want. You could go out, pump water with it. A lot of things could be good from that. And how much energy would you get from that? Well, this is, again, from them, not me. These are the max showers. Energy. The U means energy, maximum energy. These are the number of the electrons in that shower. Max E means electrons, maximum electron number. All right, so it's coming in. What happens? As it comes through, you got almost no showers here. You got very little energy. There's no energy to it. It's coming in. And it starts to get a little more and more energy as it's bouncing back into something that's pushing it back. And then it hits the Venturi and 3,000 times more than down here. Now, what happens to the number of particles? This is the energy that the thing is putting out. It's what it sounds like to me. This is the number of particles. So as it comes in, there's not a whole lot of them, but they keep banging and banging and banging and banging and banging, and they keep creating a bigger shower. And just before the Venturi, they drop right off to nothing. And as they come out of the Venturi, you're way up here with particles. You see that? Again, that's not my diagram. That is from, I believe it's from CERN, Large Hadron Collider, but I could be wrong. It's one of them, and I don't. If anybody wants to contest it, they should contest it, because I'm showing what I am picking up from the big guys. I like to work with the big guys. They don't like to work with me, but I use their information, and then I cull from it what I can see based on our research. And I can see that these are photons. And they come green, red, blue, they come in all colors, and they're always the same particles, and they're always made of two dipole electrons. And dipole electron flood theory is now the theory that has to be disproven. I've shown. Now somebody's got to come along and say, no, Roger, you're wrong because of this, that, and the other thing. So far, that has not happened, and I don't think that anybody can do it, so I doubt if it ever will happen. But if you know anything about physics, and you can come up with a reasonable argument, I would love to hear it. And I'm serious. I don't want to hear it just to say, oh, I want to hear if I made a mistake here. I don't think I did. And this accounts for everything. It accounts for gravity, it accounts for dark matter. And virtually everything they're saying right now is just not true. These dark particles aren't passing through you trillions a second. No, absolutely not. They're banging into the fields that are on you, and they might push in a little ways. And the harder you hit, more will go deeper. And they'll go deep enough where they can kill your bacteria and everything. They kill your cells. But that's when you have high intensity X-rays and way up in this spectrum up here where you're outside of the light. You're into actual just the hardcore particles. When you get way up here, that's nothing but dark matter going into you. And they can go deep. And they can kill your cells. They can kill your bacteria. They can make you sick. That's what acute radiation sickness is. It kills all the bacteria in your body. You lose your enzymes. Well, it doesn't kill all of it, but it kills a lot of it. Enough to, all of a sudden you start throwing up. Diarrhea. Why? Bloating, gas, all kinds of things happen to you. Within a couple hours of being heavily exposed to high radiation amounts. And they actually do some of that. A CAT scan gives you what's considered to be a whole year's worth of radiation in one session. It gives you one millisievert. And you're not supposed to have one millisievert unless you could take the whole year. And it's coming a little here, a little here, a little here, a little here over the whole year. But one CAT scan, you get that whole year's dose in one sit down. I'm not sure that's so good. I would like to see a test of what bacteria is in a person's body before they get that CAT scan and what bacteria is still left afterwards. Because the bacteria make the enzymes make you healthy. All of this stuff fits together. Dipole flood theory, all of the stuff I research is everything. Because everything is a part of everything else. There's nothing that just sits in the woods by itself. All right? That's it. Thank you. Bye.